Okay, so for some of you that may still be a little bit confused about the discharge formula and how that works if I were to change the cross-sectional area or change the gradient, the velocity within the stream, let's do a couple of exercises. So if you think of a stream, let's call it this one that is here in the picture, and you know that the gradient of the stream is not changing. So it's, let's say, it's covering 100 feet every mile that it travels. So it's going downhill 100 feet every mile that it travels. And it continues to do so for a very, very, very long extent. So let's assume that that is our gradient, and that's not changing. So our velocity overall should not be changing, okay? However, what would happen if we were to increase the cross-sectional area? What would happen to the discharge overall? So, assuming again that our gradient is the same, we still are losing 100 feet every mile in elevation. But now this area that I have down here is no longer like that. But let's enlarge it about that much. What would happen to that discharge? So we know that if I were to enlarge that area, then the area part of the equation would become bigger, and hence the discharge itself would increase. Okay? Now let's look at another scenario. So now we have the same cross-sectional area in the two different scenarios of our case, but now what we're doing is that we are lowering the gradient. So now we go from, say, the 100 feet per mile to only 50 feet per mile, for example. So what would happen to our discharge overall if we were to do this? So, if we were to lower the gradient, our velocity would decrease, and with our velocity decreasing, v making itself smaller, then the discharge overall would also be smaller. So we would decrease the discharge because the velocity itself is decreasing. Okay, so hopefully with that, you guys get an idea of the relationships between the gradient, the cross-sectional area, the velocity, and what that is going to have to do with the overall discharge from a stream. Okay, so you can think of rivers as kind of like a conveyor belt. So it's going to pick up some stuff in one place and then drop it off at a different place. So they're going to be erosive, and they're going to transport those sediments that they eroded, and then they are going to deposit them somewhere else. So these features are big features that move sediment across the land long ways. And as we have seen in the past few slides, when the river goes from a higher gradient to a lower gradient, it tends to slow down. So the velocity decreases along with the lowering of the gradient itself. Also, whenever the flow widens, whenever your cross-sectional area tends to be larger, you tend to get a slowing down of the river itself. So I'm going to draw, give me a second, I'm going to draw over here kind of like a representation of how I think that looks. So if you think about this, not that. If you think about this as being your river channel, and the velocity is highest over here, wherever the water is touching the walls, tends to be slowing down. So these walls act kind of like a friction mechanism. So the water slows down near the walls, and it's fastest further away from them. So it tends to be faster higher up where the water is, and in the middle of the stream for the most part. However, if we were to have our stream bed to be a lot wider and not quite as deep, so this, okay, so this being our water, everywhere where the water is touching the bed or the sides is going to be slowed down. So if we were to calculate this amount of length, if you would, it's going to be a lot larger than this amount over here up there. So if you have the same amount of water coming through a stream that is wider and shallower, it's going to be a lot slower if you have the same amount of water coming through a stream that is narrower and deeper, because there's more friction in the wider and shallower stream. Okay? I should also clarify that before we continue on. Okay. So, having those two things in mind, that again, velocity decreases when you usually widen the flow, and it also decreases if you lower the gradient, then we can recognize a few features of deposition. So those two features of deposition are going to be deltas and alluvial fans. So deltas are these features that you're seeing over here. This is the Lena River Delta in Russia that has some gorgeous pictures taken. I encourage you highly to look it up on Google. But you see that it is beautiful how from the main part of the river over here, it kind of ends up in the ocean, and it distributes all its smaller channels into the ocean. And as you're seeing with those channels, there's a bunch of sediment that is being deposited. So the river must have much earlier, much closer to its source, eroded a bunch of sediment, transported that sediment within it, and then deposited out here in the delta. Same thing for the Nile Delta that you're seeing over here. It's harder to see the water actually in the Nile Delta itself, but you're seeing the delta right here. So all of that green stuff, it's going to be vegetation that it's rejoicing itself by the nutrient-rich sediments that have been deposited by that river. So all of those sediments, again, are carried out through the river, and they have been eroded much earlier, closest to the source of the river, and are now being deposited here at the outlet of the Nile Delta in Africa. Okay, so they're called deltas, I should say. Oh, sorry. They're called deltas because they make sort of the same shape as the letter delta, the letter Greek delta. So if you think about this as being the river and this as being the base level, for the most part being the ocean, all the sediments are going to be deposited kind of in a delta-like shape. So that's why they're called deltas. Okay? Okay. And then a secondary feature that we have that is, again, a depositional feature is an alluvial fan. So you have this alluvial fan down here, which is a beautiful example of how an alluvial fan looks. So the way an alluvial fan forms is you have a stream that tends to be ephemeral, so only active during certain parts of the year. So it's usually a seasonal stream that goes from a high gradient and a confined bank to a lower gradient and a not confined bank. So this happens a lot in mountainous terrains that go into big valleys. So actually here in the Treasure Valley, we have a fair amount of old alluvial fans. So in the foothills of the Boise area, actually, we have a ton of alluvial fan-like features, and we've actually constructed a bunch on top of those features, which is probably not a good idea. So again, I told you that alluvial fans are formed by streams that are seasonal. So during the springtime, the stream that flows through here is going to carry a bunch of sediment, and as it gets into this wider valley, since it's no longer confined, it's just going to drop those sediments in a fan-like fashion, as you're seeing down here. And then during the fall and the winter, where there's not so much precipitation and so much water coming through the stream, then the stream is not going to carry any sediments if it's even flowing. However, because it is seasonal, it's going to carry a lot of them during the heavier rainfall times of the year. So just as an example, let's go to that Boise foothills picture that we had before. So over here, you're seeing again the Maynard Gulch right here. That was the drainage basin we outlined. And then you're seeing that here at the gulch, there's a fan-like feature. It's hard to see obviously because these sediments have been constructed on, but you can also see it in this one right here. There's a fan-like feature from this other gulch right there. So why is it dangerous to build on top of these alluvial fan sediments? Well, first of all, because the sediments themselves are going to be a little bit unstable. They are not solidified. They're not lithified, made into rock just yet. They're still sediments that are loose. And so if they are saturated with water, they can move very easily. So that is one of the reasons. The second reason is that if the stream had a year of a lot of precipitation and it carried along with it a lot of sediment, then it would be depositing all of the sediments that it carried along with it along this alluvial fan. So all of the sediments would be deposited next to the houses or buildings that have been built in that area. So obviously damaging property. So it's probably not a good idea to build on alluvial fans, but we have done so nevertheless, probably without much knowledge. So again, deltas and alluvial fans are both depositional features within the streams, or by the streams, I should say. Oh, I should also mention that streams are very big transporters, as I have said before, and you can see that in some streams, such as the Mississippi or even the Amazon River. You can see that they're very murky. You can even see the sediment itself. They're not clear, so the sediment is floating within the stream. So it's easier to see that those streams are very heavily full of sediment. And we'll cover that in the next couple slides. When we talk about materials that are being transported by the rivers, so not the materials or the features that are depositional, but the materials themselves that are being transported within the stream, we have three different types of loads that are transported. So the first one is going to be the bed load. So as you're seeing here in the diagram, the bed load are for the most part big cobbles or big gravels that move throughout the bottom of the stream. So they can either kind of drag along or they can sort of saltate, it's what it's called. So the particles kind of bounce up and down and then they bounce up and down, but they never are quite floating within the stream. They're always either dragging or kind of bouncing. So that's going to be the bed load. Second type of load that we have is called suspended load. So that's going to be finer kind of silts and maybe even mud, clay-sized particles. So those particles are usually what make a river kind of muddy looking, kind of murky water. So the suspended load, as the name kind of says, is going to be sediment that is traveling through with the water, like carried by the water in the stream, and it is suspended. It is floating within the water itself. It's just traveling while it's floating. So it tends to move faster than the bed load. And then we also have a dissolved load. So dissolved load is going to be particles that are now not visible to us. So for the most part, the dissolved load is going to be really just in the atomic kind of aspect of it. So it's going to be different anions and cations that are going to react chemically with other things further downstream and perhaps make different minerals as the water either evaporates or gets settled or whatnot. So the dissolved load is not visible and it tends to just be different ions. Okay, so real fast, I want to show you this video that kind of shows you the types of load that are moving. So in this case, it's mostly bed load and suspended load, but let's watch just a little bit of it. So you're seeing that those cobbles on the bottom are either just kind of being dragged or they're actually bouncing. They're saltating is the term for that. And then as you get further into the video, it gets a little bit more murky and murky because more suspended load is being incorporated within that flow. So this is just a model, it's not an actual river, but it gives you an idea of how it's going to look for high discharge, for times when the river has a high velocity.